this example, we're going to take a look at applying Stokes' theorem in a few different ways here. In this problem, we have the sphere x squared plus y squared plus z squared is 2, and the paraboloid z equals x squared plus y squared. And we have a curve of intersection of those two. So if you could envision where the paraboloid and the sphere intersect each other. And I found it down here algebraically. So if we look at the intersection, if I substitute the x squared plus y squared here, I get z equals -2, which is extraneous, and z equals 1. So they intersect in the plane z equals 1. And putting z equals 1 back in here, I get x squared plus y squared is 1. And so the intersection here is, this circle. Okay, so C is the curve of the intersection with those two oriented in the positive direction, so oriented positively. So if I look down from above, that's counterclockwise. So here is what we've got. Now, I didn't actually ask a question here. I want to find the work. Okay, so I'm going to do that a bunch of different ways. First of all, just as a quick review, directly. If we're going to do it directly, we have to parameterize this curve. Well, this is a unit circle, so x equals cosine of t, y equals sine of t, and z, well, z is 1. So z is 1. And so f, if we put into f our x and y and z and put it all in terms of t, I get x minus y, which is cosine t minus sine t, y minus z, which is sine of t minus 1, and z minus x, which is 1 minus cosine of t. And r prime, the derivatives here, are minus sine of t, cosine of t, 0. And so that dot product is minus sine of t cosine t plus sine squared of t, dot product here, minus sine cosine plus sine squared, sine cosine minus cosine. So plus sine t cosine t minus cosine of t, and then 0 here. So sine cosine minus cosine, yes, that goes, I get sine squared minus cosine. So sine squared t minus cosine of t dt, and this is the whole circle, so t goes from to 2 pi. So that's not too hard to do directly. But let's see how we could use Stokes' theorem. And let's suppose I wanted to do Stokes' theorem, and I want to use the paraboloid. So Stokes' theorem says that for any surface that's bound by this curve, so as I was saying, it's like this is your bubble wand, and if you blow this way and you get this blue surface here as your bubble, that's what I'm going to do. So Stokes' theorem says, once again, that the line integral is the flux of the curl. And so to do the flux of the curl, we do the curl dot the gradient of g over d. Okay, so in this problem, if we're using the paraboloid, then our surface is z equals x squared plus y squared. So we're looking at this as z as a function of x and y. We get everything on one side. And this is what I call g in the shortcut. The gradient of g is negative 2x, negative 2y, 1. This is where I ask whether or not that's what I want, positive 1. So the orientation of the curve is positive, and we're told the orientation of the surface must also be positive. And so, yes, this is what we want. We want positive orientation. Okay. Now, something that is not in your book, but just so that you're aware, if you want to make use of it, it doesn't have to be positive orientation and positive. It just has to match. So if this is positive orientation, you want positive orientation. If this is going the other way, negative orientation, then you would choose negative orientation. But the way that your book does it is if the curve is negative orientation, we'll just find it for positive and then take the opposite of the answer at the end. Okay, so either way, I don't want to throw too much in there, but we're going to do positive orientation for the curve, positive for the surface, so this is what we want. Okay, now what else do we need? We need the curl of f, not f, the curl of f. So curl of f I will let you compute the curl on your own, but this is what you would get, 1, 1, 1. And so now we need the dot product of these two. So negative 2x, negative 2y plus 1. So the work is the flux of the curl. So we're going to dot the curl with the gradient of g. And so that's going to be minus 2x minus 2y plus 1 dA, where this is our d. So, we're back into familiar territory. Now, I'll let you work this through. I would probably choose polar, negative 2r cosine theta minus 2r sine theta plus 1 rd theta, 0 to 1, 0 to 2 pi. Okay, so that would be another way to go. We could also use Stokes with the sphere. So in that case, the surface would be x squared plus y squared plus z squared equals 2. Now we have to be careful about this. The way the shortcut with g works is we first have to solve for z. We're just doing the top part, and then get everything on one side. And then this is our g. Okay? So that, we have to be careful about that, because when we take the gradient of this, we need a 1 with the z. All right, so the gradient of g here is going to be 2 minus x squared minus y squared, a 1/2 with a 2x and a minus. Okay, you can fill in the details there. Hopefully I got that right. And here is where I ask myself, is this what I want? Needs to be 1. Do I actually want upward? Well, yeah, if the curve is oriented positive, then the normals for the corresponding surface have to be oriented positive. Right? Sometimes people look at this and they say, but it's a closed surface. Shouldn't these be down? No, it's two separate problems. It's with this surface oriented positively, or separately with this surface oriented positively. Okay, it's not one whole thing. It's like two different ways of doing the problem. The curl is 1, 1, 1. And so our line integral, if we use this surface, is going to be that dot product. So x over the radical plus y over the radical plus 1 dA, 2 minus x squared minus y squared. Sorry, 2 minus x squared minus y squared. Hard to see it. Same region. I go polar. But I wouldn't have chosen this. This one is easier, doesn't have the square roots going on. But just to show you, you can use either. If I haven't made any mistakes, and if you carry this through, they should be the same answer. Same here. Now in this case, you're probably looking at this and going, you know, this one was easier directly. Sometimes they are. Sometimes they are. Sometimes these are much easier, depending. Sometimes this is impossible. Options, gives us options. All right, the other thing we can do here, which I mentioned when I set it up in class, is, and is sometimes easy to miss, is this, we found out that this curve intersects in the plane z equals 1. So that means that this surface right here is the plane z equals 1. And because Stokes' theorem says we can use any surface that is bound by this curve, this is a surface that's bound with that curve. And so I can use Stokes with the plane z equals 1. And that is much easier of a surface than either of the other two. So if we're going to do that, then z equals 1 is our surface. Our gradient of g is 0, 0, 1, and that is what we want, positive orientation to go with the positive curve direction. Our curl is 1, 1, 1. By the way, I should make sure it's clear that when we do this integral here, a lot of times, often, the curl has variables in it. And so if there were any z's in it, we'd have to put in the z equals 1. Same if it was here. If there was a z in my integrand, we'd have to put in z equals x squared plus y squared. Okay, so this dot product is 1. And so that is just the area of D, and that is pi. That is the easiest way to do that problem.